Hi everyone, I am Juan Carlos, working for Rittal in Germany. Today I will present this work stream. This is the rear door interface for ORV3. The purpose of this work stream is to generate or write a white paper with the points we will describe after this in this presentation. There are three points, three focus we want to develop. But this is the cooling and mechanical interfaces, the electrical interfaces, and the communication interfaces between the ORV3 and the rear door. Most of you knows these three different deployments are the traditional rear door, which is the focus is only to cool down the air without taking into account the direct-to-chip cooling in the rack. The air-assisted rear door heat exchanger, this is the next logical step going into the direct-to-chip cooling. In case you have not water in the row, you can deploy direct-to-chip cooling using a rear door and a pumping unit in the rack. Next step will be to use a traditional rear door and using DLC, using facility water in the row. So in this white paper, we want to work with the typical hydraulic connections. Could be hoses, copper, stainless steel. Hoses is the most common connections between the rear door and the rack because are flexible and you can deploy it really easily. You can cut it in the facility if you need. For copper and stainless steel is most difficult, have some advantages, but also disadvantages. When we define the material we want to use, it's important to define what is the maximal speed you can run through these pipes. It's not the same to use stainless steel, copper, or rubber pipes. With the maximal velocities, it's more easy to define the maximal flow rate, and with the maximal flow rate, we can define the maximal cooling capacity through the pipes. The dimensions of the pipes are really important because we have to put the pipes through the frame, and the frame have to be larger or shorter depending the size of the pipes. The position of the hoses, in one side is the cold manifold, the warm manifold, but we can decide where to pass the hoses in order to get more space for the air and reduce the pressure drop. There are more accessories we need to clip the hoses, how to fix it, to avoid that the air is going up from the frame, and give an overview of the technical combination between the rear doors and the rack. Like I said, there is three typical materials we can use. EPDM hoses, the copper pipes, and stainless steel. Depending the hardness of the pipe, you can use or you can deploy more speed, more velocity for the liquid or less. Here you can see in the Parker specification for piping for EPDM hoses that depending if the hoses are in vacuum or is the pressurized lines or return lines, you have different limit in the speed of the water. But in both cases, if we are working with DLC, usually we have positive pressure. We are not working with vacuum, and we have always pressurized lines and return lines. So the most logical speed for the maximal speed for the water would be 3 meters per second, regarding this specification from. from Parker. Like I say, it's possible to use also copper and stainless steel, but this is much more difficult to connect it because are not flexible, and you need some tolerances, and therefore it's PDM hose is the most logical way to go ahead. So once we define the maximal speed, we define the materials, we can define also the maximal flow rate, and with the maximal flow rate taking in account the 1.5 liters per minute per kilowatt, which is 10 degrees delta T between the cold plates, we can define the maximal power we can deploy with this size. For example, you can see here for hoses, EPDM, if the diameter is 1 inch, the inside diameter will be 25.4, and for that we are able to move 91 liters per minute, means 61 kilowatts. The same if we are using 2 inch, the inside diameter will be 50.8, the maximum flow rate is able to be 365, and the maximal cooling power 243 kilowatts. It is important because depending the use case of the customers, they will deploy 100 kilowatts per rack, 200, 300, and then we have to adapt the hoses for this use case. You can see if it's possible to use stainless steel, you can increase a lot the cooling power using the same sizes. When we decide which hoses we need, we are able to adapt the frame. The tip of the frame is important because we have to put the hoses through the frame. In the open rack V3, there are not holes for the hoses, so we have to put the hoses between the rear door and the open rack V3 through the frame. This frame, if we are using, for example, 1 inch, and we have a cooling power for DLC of 61 kilowatts, we need a frame depth from more than 36 millimeters. The same for 2 inch, 243 kilowatts, and more than 63 millimeters. In case the customers want to use two-phase liquid cooling, then there's maximum fluid velocities defined. For the vapor side is 15 meters per second, liquid side 2.5 meters per second. And yeah, it means that for 35 kilowatts load, the vapor line will have 40 millimeters inside diameter or 14 millimeters inside for the liquid line. When we define the frame, the dip, the hoses, diameter, power, we have to look how to deploy these hoses through the frame, because usually in this case there is the air-assisted rear door heat exchanger, and that case is not critical. But if we are using, for example, a hybrid deployment, we have 4 pipes going out and in, and the problem could be that they will block the air. To be able to let more place for the air to go through between the servas and the rear door, we could put the hoses behind the manifolds to allow the air go through this space between the DC busbar and the manifolds. You know, the pressure losses in the rack is proportional to the consumption of the fans. So if we are able to reduce 10% the pressure losses in this space, we will almost reduce the power consumption by 10%. So it is important to take into account. Open rack V3 have some defined position to fix the rear door. The same could be for the frame, and we'll be interested if we are able, also if we put the same connections in the frame, to be able to put the rear door in the frame that in the same way that we are fixing the rear door in the open rack V3. next effort. The next months we have to work in the electric interfaces to define the electrical power, which kind of voltage we want to use. It's logical for OpenRugby3 to use 48 volts from the DC bus bar, but there is another question how to get this power, because the DC bus bar is need a connections, and no connections are defined to be attached and connected to the rear door. And this is something we have to go ahead. Which type of cables we are using, the routing, and how to fix it in the rear door and OpenRugby3. For the communication interface, the same. Find the cabling we are using, and more important is the route. You know there is not many spaces inside the OpenRugby3 to put the cable between the rear door and the front of the OpenRugby3, and will be a challenge to do that, because one solution could be put the cabling outside the OpenRugby3, but this is really not nice to have. We have to find the way to put the communication cable from the back of the OpenRugby3 to the front. Here I'll let you some links with many presentations and white papers about these issues we discussed here before, about the hoses, the TCS loop, and so on. I think it is really interesting. You can take a look here. Please, if you are interested in this rear door heat exchanger group, the cooling interfaces, yeah, please come. We meet every month, and for the groups every single week, I think, or 2 weeks. So please join us, help us to develop this group. So thank you very much.